Let's look at our third case where we have complex and distinct poles. And so this is the last case that we're going to consider, but remember there is also a fourth case of complex and repeated poles. So I think it's easiest for this case to start by considering an example. So let's say we want to find the inverse Laplace transform of this function f of s shown below. So we have 100 times s plus 3 in the numerator, and then quantity of s plus 6 times s squared plus 6s plus 25. And so if we try to factor out this s squared plus 6s plus 25, we'll see that the roots of that function are actually complex. So if we write this out in our three terms, we're going to have a k1 over s plus 6, so that's going to be a real pole at -6, and then our two other ones are going to be complex. So we're going to have s plus 3 minus j4 and s plus 3 plus j4. And so we'll have k2 and k3 associated with those. And so we see now we have these complex poles. For instance, here, our pole would be at s equals -3 plus j4, and here our pole would be at s equals -3 minus j4. And so we notice that these two are complex conjugates, and so we'll come back to that here in a little bit. So our basic process is going to be the same as case 1, it's just now we're dealing with complex numbers. So same as case 1, just with complex numbers. Okay, so of course finding our k1 value is not going to change at all because we don't have to deal with the complex parts there. So for k1, we're multiplying both sides by s plus 6 and evaluating at -6, and so that's going to get rid of these two over here. And so on the right, we're just left with k1, and so that's going to be equal to 100 times s plus 3 divided by that s squared plus 6s plus 25, because we've canceled out the s plus 6, and now we evaluate at s equals -6. And so what we get is 100 times -6 plus 3, which is -3, and plugging in -6 in that denominator and evaluating, we get 25. So overall then, we get that our k1 is -12. Okay, so moving on to our k2, now we're going to be dealing with our complex numbers. So the same basic idea, in this case, let's say we multiply through by that s plus 3 minus j4. So we multiply through by this term. So we're looking to find k2. And so what we have remaining on the left then is we're going to have 100 times s plus 3 in the numerator divided by our s plus 6 is still around this time. And we also still have our s plus 3 plus j4. And so we're evaluating this at s equals -3 plus j4. And so it's the same basic idea as what we did for k1, it just looks a little bit different. So as we plug that in, we have 100, and now -3 plus j4 plus 3 is going to result in just j4. In the denominator, we have -3 plus j4 plus 6, so we're going to have 3 plus j4. And then finally, -3 plus j4 plus 3 plus j4 is going to give us just j8. And so from here, there's a lot of different ways that you can sort of simplify this complex number. I'm going to show you the way that I prefer to do it, but that certainly doesn't mean it's the right way, the only way, or the best way, or anything like that. So in the numerator, we can multiply that through, of course, and we see that that is just j400. In the denominator, we multiply through that j8, keeping in mind that j squared is equal to -1. So our j8 times j4 gives us 32j squared, or -32. And then j8 times 3 is just plus j24. So we can perform this division in our rectangular form of our complex numbers, but again, this is just my preference, as I usually like to take it to our polar form. So for our j400, that becomes 400 angle 90 degrees. And in the denominator, that negative 32 plus j24 becomes 40 angle 143.13 degrees approximately. And so if you do have any questions about any of this complex math, please do let me know and I'll be happy to sort of give some more details on any of that that's unclear. So now we have 400 divided by 40 to give us our overall magnitude of 10. And we do 90 minus the 143.13 to give us our overall phase angle of negative 53.13 degrees. And so we can write this in a couple different ways. We can write this as 10 e to the minus j 53.13. We could also write it as in rectangular form. If we keep stored values, that comes out to be exactly 6 minus j8. So these are the values, so I'm going to circle this one, but all of these represent our values for K2. So it's going to be the same type of thing for our K3 as for K2. So for K3, we have 100 times s plus 3. And in the denominator, we still have s plus 6, but now what's left is going to be our s plus 3 minus j4. And now we're going to be evaluating at s equals negative 3 minus j4, because again, coming back to this top one, we're now looking for our K3, so we've multiplied through by this, and we're evaluating at this value here. So plugging those in, we see we have 100, and then negative 3 minus j4 plus 3 is going to give us a minus j4. And in our denominator, negative 3 minus j4 plus 6 is going to give us 3 minus j4. And then finally, negative 3 minus j4 plus 3 minus j4 is going to give us a minus j8. So again, there are several ways we can analyze this, but going ahead and multiplying through that numerator, we get negative j400. Again, keeping in mind that our j squared is negative 1, we have negative j8 times negative j4, which is 32j squared, which becomes negative 32 again. And this time we have negative j8 times 3, which is negative j24. Converting that to polar form, I get that my K3 is equal to 400 angle negative 90 degrees. And in the denominator, I have 40 angle negative 143.13 degrees approximately. Dividing 400 by 40, I get my overall magnitude is 10. Negative 90 minus a negative 143.13 gives me 53.13 degrees. And just like with our previous one, I can write this in a couple different forms. I can have 10 e to the j 53.13 degrees, or I could take it back to rectangular form of 6 plus j8. So this would be our K3. So an important thing to note is that, and I think it's easiest to see from these forms here, is that our K2 and our K3 are complex conjugates. So K2 and K3 are complex conjugates. And so that just means they have the same real part, but opposite imaginary part. So they both have a real part of 6 in this case, and then a magnitude of the imaginary part is 8, but it's opposite in sign. And so what this means is that in practice, we only need to calculate one. So for instance, we could have calculated only K2 and then said, well, we know K3 is a complex conjugate of K2, so we know it has to be 6 plus J8. So we only need to calculate one. So that being said, you might still want to calculate the second one just sort of as a double check to make sure you didn't make any errors. But in terms of, if we're assuming we've not made any mistakes, then there's no need to calculate that second one. Another thing to note that in physically realizable circuits, our complex poles, like we saw up here, are always going to appear in conjugate pairs. So if we come back and we look closer at these poles here, we notice that the poles themselves are conjugate pairs. And so our conjugate pairs are the reason that we have complex conjugates for our coefficient values. So in our real systems, we're always going to have these complex conjugate poles, which means that the coefficients are always going to be complex conjugates as well. So the takeaway from that is ultimately we only need to be able to calculate one, but you might consider doing the second one just as a double check. Okay, so now that we have found our K1 through K3, we can rewrite our f of s equation. So our f of s is equal to negative 12 over s plus 6 plus, and now over our s plus 3 minus j4, we're going to have 10 e to the j. So sorry, this is going to be 10e to the minus j, and let me make sure so this one corresponds to here. So minus j, 53.13 degrees. And then finally plus our 10e to the j, 53.13 degrees. And that's divided by s plus 3 plus j4. And so this is a little more complicated to deal with, but ultimately we can just treat these values up here in the numerator as constants. So let's say these guys up here we're going to treat as constants. And then we can use our same shifting property that we've done before, where now instead of just an s plus a, our a is some complex value that has real and imaginary parts. And so if we do that, we can find that the inverse Laplace transform of our f of s, which is equal to our f of t, is equal to, so we have negative 12 e to the minus 6t plus, and again, remember we're just treating the term circled in blue as constants, so we have 10 e to the minus j 53.13 degrees, which is just kind of along for the ride due to our scaling property. And then we have e to the minus 3 minus j4 times t plus this other blue circled term we're treating as a constant, 10 times e to the j 53.13 degrees times e to the minus 3 plus j4 times t, and then all of that multiplied by u of t. Okay, so I think you would agree in that this is a pretty ugly form to deal with. So typically we don't want to have all of these j terms floating around. So typically don't want our j terms in our f of t. So what we're going to do is we can use this fact that our coefficients are complex conjugates. So we know that all of this information here, we basically have complex conjugate poles and complex conjugate coefficients. And when we add complex conjugates, we know that the imaginary part goes away. So let's take a closer look at just this imaginary part right here. So let me actually undo that so I can copy this down here. So focusing just on this imaginary part, I think I'm going to have to take that as well. Okay, so let's focus on this imaginary part. And so what we want to do then is we want to, and so let me actually write this out a little bit different. So let's ignore this for the time being. And let's say, again, I'm still just focusing on this imaginary part here, but I'm going to write it a little bit differently. I'm going to take apart that negative 3 in the j4 terms. So what I can say is I can say for our imaginary part we have 10 e to the minus j 53.13 degrees, e to the minus 3t, and e to the j 4t. So that's our first term, and then we're adding that to 10e to the j 53.13 degrees times e to the minus 3t times e to the minus j4t. And so what we want to do then is we can factor out common terms. So factoring out common terms, what we see is we have our 10 and our e to the minus 3t is common to both of these. So we get that this is equal to 10 e to the minus 3t times e to the j, and I'm going to combine these two exponentials so that we have e to the j times 4t minus 53.13 degrees plus, and I'm going to combine the terms as well from our second one, so we have e to the minus j 4t minus 53.13 degrees. And so why am I going to all this trouble to sort of massage these equations around is, well, in this form, now what we can do is we can use Euler's identity. And so by using Euler's identity, we can more clearly see what's going to cancel out. So we have 10e to the minus 3t, which is still just hanging out front here. And then using Euler's identity, what we can say is this first exponential term becomes cosine of the argument, 4t minus 53.13 degrees, plus j times the sine of the argument. So 4t minus 53.13 degrees. Similar thing for our second part. So for this second exponential term, using Euler's identity, we have this is equal to cosine of the argument, which is 4t minus 53.13 degrees. And now because we have a minus j in the exponent, this becomes minus j sine of the argument, which is 4t minus 53.13 degrees. So we get something that looks like that. And we notice that all of these cosine and sine terms have the same argument. And so we can see that we have a plus j sine and a minus j sine, which are going to cancel out. And then we just have two of the cosine terms, which are going to add together. So we get 10 e to the minus 3t times 2 cosine of that argument of 4t minus 53.13 degrees. So what we can do now is we can take this and we can substitute it back for our imaginary part in this expression. So if we do that, we can now rewrite our f of t is equal to, so we have negative 12 e to the minus 6t plus 20 e to the minus 3t times cosine of 4t minus 53.13 degrees, and all of that multiplied by our unit step function. So I think we can all agree that that is a lot easier to look at than our previous term where we had all of those exponentials and all of those j's floating around.